So good afternoon to everyone. Myself Manidip. I'm doing my PhD with Nabyandu Das sir, and I would like to thank Rakesh sir for the conference as well as for the opportunity to present our research. So the title of our topic is bulk boundary correspondence and higher order topology and bulk boundary correspondence in a two-dimensional SSH model. So these are the outlines of our topic, which is topological insulators. What is a topological insulator? And a one-dimensional SSH model, which is a toy model, which everyone jump in to understand the topological features, and a two-dimensional extension of this one-dimensional toy model, and experimental realizations of this whatever the particular extension is, and reference and suggestions. So coming to the definition of topological insulators, everyone is asking the question, what is topology in this and what is a topology? So to give a good definition, the way we refer topology in this here is the mathematical classification of the electronic branch structures with a global property of the system. So under the continuous deformation, by changing the parameters in the Hamiltonian, there won't be the global properties that we are looking of for the band won't be changing, which is invariant. So that is how the topology comes in condensed matter one way. This is my understanding. And when we have a periodic lattice and we have this wave function, the geometrical phase can be taken as the global property, which with this geometrical phase we can try to derive some invariants which define the topology of the system. And so if we change the system's parameter and there is a continuous deformation in this global property in the phase, and if the phase goes to 0, then we call it as trivial topology. And if the phase doesn't goes to 0, when you change this when you have this continuous deformation, we call it as a non-trivial topology. So when there is a trivial and a non-trivial topology, there should be a topological phase transition which happens. And one way of looking in this topological phase transition is by looking at the band closing phenomena. And now I come to the definition of topological insulator. Topological insulators are a d-dimensional materials which has an insulating bulk, and after a topological phase transition, it has d-1 conducting surfaces, or a d- conducting boundaries in a precise way. And so one of the key toy model we use is the community use is SSH model. And before going into this SSH model, I would like to point out the Nobel Prize in 2000 chemistry, where we have this development discovery of developments of a conductive polymers. So this is one of the person, Heiger. He is the one out of all three. He is the one who developed the SSH model. So the full form of SSH is Schuh-Schiffer-Heiger model, and it was developed in 1979 to explain the conductivity nature of the polymers. So since yesterday Saurav sir already gave a good understanding of SSH model, I would like to run it quickly about the SSH model, and then I will introduce our work. So in SSH model, it is a one-dimensional lattice structure which has two atoms in its unit cell, which is indicated by this red and white. 1 minute, how can I use the pointer?
For the light.
Which one, sir? Okay. So these are the atom white and red atoms, and the hopping here is within the unit cell. The hopping we denoted it as V, and W is then between the unit cells. And the Hamiltonian in a real space can be written like this. And so now what we try to do is the another interesting phenomena with this topological insulators is the bulk boundary correspondence. That means if you can able to study the bulk, you can able to predict what is happening at the boundaries. So to study the bulk regularly, what we try to do is we try to connect these edges and we'll make it a periodic system, and we try to do the Fourier transformations in momentum basis with my basis as k and alpha, with alpha goes to a and b, the sublattice. And after doing the Fourier transformation, this is my Hamiltonian, and diagonalizing this Hamiltonian, we give you the energy spectrum as well as the eigenvector. And this eigenvector have this tan inverse of W sin kx by V plus W cos kx. And these are the dispersions relations which Sauros are already showed. And now what we try to do is we can see that there is a band closing phenomena at V is equal to W. So one of the which I previously mentioned, when V is equal to, when the band closing phenomena is happening, that there might be a topological phase transition. So is it actually there in this or not? So we try to understand it. We need to find a global property which we can see those phenomena. So one of the global properties coming from the phase of the system, whatever the phase of the wave function. And when we take this electron from minus pi to pi in the Brillouin zone, since it is a one-dimensional system, our Brillouin zone is a circle. So minus pi is identical to pi. And if we try to see how the phase evolution is happening, we will calculate this Berry curvature, and then we'll try to integrate this Berry curvature along the Brillouin zone, which gives us three different situations. When V less than W, it gives us 1, V greater than W, it gives us 0, and undefined when there is this band touching phenomena happen. So now we find a global property where we can able to see that it's a topological system. So at V is equal to W, what happens is in the wave function, because of this, when the band touches symmetry, the band will get inverted, and there will be wave which involves a zero energy state within that wave function. So that phenomena happens. So which we see it in the next slide. So since it is a 2x2 matrix, we have this Pauli decomposition where we can write it as a Dirac Hamiltonian, where Hx and Hy, which we can see this, we see at the phase, on the phase, and V plus W as the denominator in the phase. So now if I am able to try to plot Hx and Hy, since it is a closed boundary condition, and I have my Kx and Ky space, which is my base space, and I'll try to evolve my electron in this, and I'll try to see how Hx and Hy goes. So now if I can see this at V less than W, this Hx and Hy will circles around the origin. So when I change the system parameters V and W, this circle always shrinks or expands, but it cannot be collapsed to 0. Like it cannot be gotten to 0 because of the zero energy, this thing. At the origin, Hx and Hy is equal to 0. Root over Hx square plus Hy square is the energy of the system. And in the other phase, it exactly touches the origin. And we don't know after in what, if you change the system's parameters, we don't know whether it will be in a topological phase or non-trivial phase. And this we can at this figure we can shrink it to 0 without any this thing. So and so now we have seen that there is a topological phenomena here. We studied the bulk, and is there anything can we connect it to the edges? So now we have this bulk boundary correspondence. So what we try to do is we try to analyze the finite Hamiltonian, where we try to write it in a matrix form, and at extreme cases what we can see is at this column, so this one and this one goes to 0. These are the contributions from the zero energy states. So if you look at this pictorially, what we can see is we can see a dimerization in the system in two different cases. In V is equal to 0, we can see a dimers, but we also see a zero energy state related to this. In this case, there is no zero energy states. So then there is this, okay, coming to symmetries of the system. Apart from translation symmetries, we have this time reversal symmetry, inversion, and chiral symmetry. Because of these symmetries, we have this Kramers degeneracy because of time reversal, band inversions because of this inversion symmetry, and the spectrum is symmetric around the zero energy states because of this chiral symmetry. And one of the main reason to have this chiral symmetry is, I forgot to mention, is because we are not allowing the electron to hop from A to A or B to B. So we cancel those, like we don't allow the electron to go. The electron can only hop between A to B within the unit cell or between the unit cells. So now to establish a bulk boundary correspondence, from the bulk we are trying to derive a topological invariant, which is a winding number which has 1, 0 and undefined. And from the boundaries we have this zero energy modes. When winding number is 1, we see a couple of zero energy modes, and winding number is 0, we don't see any zero energy states. Now with this knowledge, what we try to do is we try to extend a two-dimensional SSH model. So this is a peculiar, or this is a unique kind of extensions, because generally what people try to do is they'll try to stack it in either x direction or in y direction. So what we did is we looked at the system we stacked it in a diagonal direction, where the diagonal chains are SSH chains with the regular V and W hoppings. And when we stack this chain, we moved it to one unit cell and we stacked it. So between the chains, we introduce a new hopping, which is indicated by the dotted line T. And the Hamiltonian in the real space can be given like this, where mx, my are the points, x and y coordinates of the lattice, and nx and ny are the number of lattice points in x and y direction, and vw are the regular hopping parameters, and t is the interchain hopping. In between the chains, what is the hopping? So now we'll follow this thing. So we'll try to apply a periodic boundary condition by closing the system in both the directions, where we can apply a Fourier transformations in momentum basis. So our parametric space here will be a two-dimensional Brillouin zone, which is a 2D torus, and the momentum goes from minus pi to pi, kx and ky, and the bulk Hamiltonian can be written like this, where h, kx, ky be written like this. So this term is because of this unique stacking, this is the term which has a significant role in this in the higher order. So this is the dispersions, and this is the vector, this is the state vector, block vector, and now yes sir, between the chains, yes.
So the thick line is.
Sir, this is W.
Yeah.
This is V. This is T. So we do this Fourier transformation. We have these dispersions, and then we try to plot these dispersions. And there are 5 conditions in which we can see a band touching in one of the case, which gives a hint that it might be a topological material, and there will be band opening. So these diagrams will look symmetric around this diagram, but this one is the point where the band has a very what you call low gap, at less gap at some points. And if I take this as my Brillouin zone, so I have this 4 points where my band touches. In one case, the band gap at this and this is very small. In another case, the band gap is at this and at this is very small. That is what these 2 diagrams are. They might. Yes, I will give that condition here. When the individual chains are in non-trivial topological phase, when the stacking chains, individual chains are in non-trivial topological phase. Okay, your question to answer at what? That is where when V is equal to W and T is equal to V plus W by 2. Yes, that is where the phase transition happens, topological phase. And yes, sir, diagonal chains. Yeah, stacking in the diagonal direction. So because of this band touching phenomena, we can see that there is a topological phase transition. And to further look into this, whether it is there or not, what we need to do is, and again we looked at the symmetries of the system. Apart from crystal symmetry, which is a new symmetry than the regular one-dimensional change, we have the old symmetries which we talked in the SSH chain. So, and since we have this time reversal, inversion, and chiral symmetry, and if we look at the classification of periodic table of topological insulators, when the system has time reversal, inversion, and chiral symmetry, in 2 dimension we don't have a topological invariant. So this was the issue that we faced in the initial time, and what we try to, and in general, if it is a 2-dimensional system, people generally use Chern number, where they use the Berry curvature formalism to have a topological invariant. But what happens is, because reversal and inversion symmetry, the Berry curvature becomes an odd function, where when you try to integrate it over the Brillouin zone, it gives you 0. So it failed to capture the topological properties of the system. So now what we try to do is, we have this basic understanding. What we need to do is, we need to adiabatically change the phase in a closed loop. like wave function in a closed loop, then only we can get to see a global property. We can get to see. So with this motivation, what we try to do is we try to plot a color mapping bit.
There may be some higher topological how do we, I mean, this, there is a proof that you have no, like, I don't know, I mean, you can have some higher homotopy groups or higher homology groups, right? Like, why they're all zero?
I don't understand the topology of the surface she is considering.
Sir, we have this base topology.
Is here, is it a torus?
I remember Saurabh said at this talk you can't have anything higher than this, right?
He said they are not yet discovered, but he said it might be a trivial thing. We don't. I asked the question in the talk, when the system has all this kind of symmetries, what do you mean having a zero? And he said we didn't explore it in the direction, and it might be a trivial. It's trivial.
All there is that.
Because in torus, there are, because of phi1 and x1, is it, there is a whole number of other invariants you can write down.
Sir, this is what the community.
Torus, I see what's pointing out.
What is T2, C2, and S2?
The square of this time reversal symmetric
Charge conjugation and S is
inversion and
this is parity.
yeah, and time reversal. So, sir, I will look into this and I'll see whether when this kind of this thing is there. So our base space is torus, the Brillouin zone. So from there we have this wave functions, and when we try to go across this torus, the wave function will start evolving, which has this kind of phase where we cannot reduce. That is how topology involved in our discussions.
If it is T2, then they can only have non-trivial H2.
Sir?
So I'm
Okay.
Response to your question of higher topology.
In the stores, yeah. But you still have two generators for your farm. I mean,
No, but
he's
the
using some
question is
conditional T2,
whether,
C2.
whether pi1 appears in the game or whether it is H1 that appears.
Can I say, well, you can have both H1 and H2.
Yeah.
You cannot say of a magnetic monopoles. The fact that your connection is zero means that the connection is zero. Maybe you are not working with the monopole bundle, so you get zero, or you are choosing the wrong connection. Because there is certainly a torus, two-dimensional closed surface like this, as U1 bundle, the monopole bundle, no question about it. And in addition, there is a whole lot of H1 that is
There's only
one thing number bundle. I'm just saying,
there's only
universal tower is R cross R, huge thing. You know? So definitely there are this bundles correspond to Z H1.
So since we are not that rigorous in the mathematics, so we try to to solve
we
this.
can come back to this point. No?
Yeah, sir.
Maybe we can come back.
Yeah,
to
we
this
can come back and see.
discussion of-
It will be helpful for us also because it.
Sure.
Yeah, sure.
Come back to this point.
Sure. So we have this zero. So what we try to do is we try to look at the phase evolution of the system in 4 different cases. So when the trivia one is v equal to w, t is equal to v plus w by 2. We didn't look in that case, but we looked at all the other cases. What we saw is there are certain paths which are embedded in the torus, which are one-dimensional paths, where there is a 4 pi change in the phase. And in some paths we can't able to have a 4 pi, and in another topological phase it has a 2 pi change. So like that I have a 4 pi here, certain paths gives me 4 pi and certain paths gives me 2 pi in this, then there is no phase change. So from that we can able to identify some set of paths in K space which are one-dimensional paths embedded in a two-dimensional torus. Generally, the way people try to solve this problem is they take a periodic condition in either the direction, so which gives me a configuration of a cylinder in kx direction, in ky direction, and then they try to go in individual directions and try to track the outer product of this with the topology for the invariant. So that is what Saurabh Basu sir also suggested us. But our intuition says that if I take this thing and we have a very good property of bulk boundary correspondence. We were unable to explore the complete bulk property if I able to derive an invariant with this kind of setup. So what I try to do is we try to look for certain paths in this torus, a one-dimensional paths. So when I get to, so there are 4 band touching points, which is delta 1, delta 2, delta 3, and delta 4. And if I try to take this path from delta 1 to delta 3, it's a diagonal path where Deeptiman Sen's R's paper, he used this diagonal path to define a diagonal winding number. So what we carefully observed is we can continuously transform this green path to this blue one, but we cannot continuously transform this yellow to blue one. So to give it a very this thing, I have if I can take this yellow path, it is nothing but in the torus we have 2 perpendicular circles which are at the point, which are sticky at the point. So now if I want to deform this into a single path, I need to cut and rejoin this yellow path. But if I take this blue and green, we can continuously deform them without any cutting or any pasting. So that kind of paths we identified, and that paths are giving us a windings like this. So yes, sir.
You cannot without cutting them.
Sir, how? Yes.
I think the diagonal one corresponds to 1, 1.
Okay. Thank you.
These 2 cylinders
Yeah,
that we do is 1, 0 and 0, 1.
Thank you.
Uh,
Yeah, correct. He's choosing different bases.
So if I look at this diagram, so the way we do it is like this Hx and Hy, and we get to see that in non-trivial topological phase of the system, that is when V less than W and T less than V plus W, the phase of the system winds around this origin 2 times. And in this other case, it winds around once, and this V is equal to W, T is equal to V plus W, it touches the origin. And in this case also it winds around in this, both these cases will give a winding number 1, this case give a winding number 2, and this is an undefined winding number. And
What is the x-axis, y-axis?
sir, Hx and Hy, the coefficients of these Pauli matrices. So root of Hx square plus Hy square is the energy.
That is a constant energy curve.
Yes. So this energy will these curves will expand or shrink when you change this V and W and T.
These 4 pictures, what are the, I mean,
Sir, this one,
ordering of the energies?
sir,
In these 4 pictures you have, are they ordered? Are they for different values of energy?
different values of V, W and T, hopping parameters.
But not Hx and Hy.
Sir, it's like if I take a condition V less than W and T less than V plus W by 2, and I have a path in the torus like the blue and the green one. So I might go like this and try to complete and come here, and then it goes to Hx, Hy. At every point in this path, we'll have one Hx and Hy which is continuous, and we'll try to close this one. So if I change this, let's take, if I take 0.4, 0.6, 0.2, I might have a circle like this. Now if I go for 0.3, 0.7, 0.1, this become bigger.
That is a curve of constant energy in the Hx, Hy.
No, sir.
So each of these corresponds to different values of E, P, and W.
Yes.
Which means they belong to different Hamiltonians.
Same Hamiltonian, but classified on the basis of the
They are restricted given one which can be mapped from one configuration to another thing by one parameter setup.
Yes,
So, but with different parameterization defines it.
yes, sir, but this parameterization will fall under one condition, right? So for 5 things, we have 5 conditions. So we have 5 different topological phases, which is classified here as 2, 1, undefined, 1, and 0. So now we get to see that there are a bulk property which is invariant with winding number 2.
It's a one.
Yes, sir.
So there is a topological characterization which distinguishes them.
The way the band closes. So this one, at one particular point, the band has a very low energy gap at these 2 pairs, and this one at these 2, other one at these 2 pairs. And when you start moving in the same configuration, these bands will start move, like the band closings will move like this.
So, in some limit, your model should also mimic the one-dimensional SSH
Yes.
model, right?
When t is equal to 0.
That's the only case.
Yes. Sir, when t is equal to 0, what happens is, the circle is there, right? The small circle which we see here, it goes bigger and bigger and become a big circle. And we have seen that observation when I'm trying to see what happens when these things are. Sir.
That is, if you are in topologically non-trivial phase, and if you take t tends to 0, you may not end up with constituent distance. That's the topological insulator is all about. Right? In topological insulator, you have these atoms, and now there is some kind of overlap of the Roy function, and you have this band and all. Now, if you go to that limit and you are in topological phase, and if you take some parameters to be 0, so you don't get absolute atoms. Okay. Here also, in that limit you won't get. Okay. But in trivial limit you will definitely.
So now we studied the bulk properties of the system, and because of this bulk boundary correspondence and topological insulators, we try to look at the edge of the system. So if I cut the edge of the system,
Why winding number is there a reason for which why winding number is upper bound? Like why did I get 3?
sir, it can be 3.
Oh, it can
So 3, we call it as variant where this z goes to 0, 1, 2. In our case,
Parameter changing.
it is only 2.
Somehow it's
It is 2 because
okay. I can ask.
okay.
Can I see? When you draw these curves, how does it show up in experiment?
In terms of corner modes.
In terms of-
In terms of corner modes, we can see the physical
in
understanding.
terms of the what are you observing? Hamiltonian, I suppose. Or what?
Uh,
What observable? Observable, not drawing curves.
Sir, okay. So experimentally, the bulk properties we derived here, experimentally they can be seen in the corner modes, the availability of zero energy states at the corners, which I am going to show. Edge modes. But because of this,
Just in the torus.
yes, that is what the bulk boundary correspondence is like. Whatever you can.
Factor out torus.
Sir, I try to look at the finite system to see in the torus structure, we have seen that this kind of phenomena is happening.
Always look for some particular kinds of transitions, is it? And the gap in transition is 0. Is that what you look for?
Sir, what about, what my question to this is, I have evaluated the bulk as well as edge independently and see is there any one-on-one correspondence between the bulk properties and the edge properties.
You know, when you tell your result to your experimentalist friend,
Yes, sir.
what will you
They will
ask
measure
him to look for?
edge corner state, zero energy modes.
How do they do that?
Sir, there is one experiment. Sir, I will come to that.
Okay, fine.
I will come to that.
Yeah, I think you should. I thought the virtual zone here, you like the cave.
Yeah.
Was a torus.
Yes, it's a torus.
That has no edge.
No,
So where did the edge come from?
I will cut the system.
Huh?
I will cut the system.
Then it is no longer a torus.
It's no longer a torus.
This discussion is in different value.
Sir, the topological insulator has a property called bulk boundary correspondence. You
That
can,
may be there in the cut system, but not here.
sir,
Not in the torus.
sir, with the torus, I predicted what might happen, what might my boundary is. See, with all these mathematical calculations and everything, what I do is I'll try to predict what will happen at the boundary. Sorry, what will happen at the boundary when I have a finite system. That is my.
Then the torus discussion seems to be misleading.
But it will. Oh, sir, it's not misleading because it is very clear that whatever happens in the bulk can predict whatever will happen in the edge.
But it kind of, sorry about
It's okay, it's okay, it's okay, it's okay, it's okay.
The torus will not happen in the bulk.
Actually, I think he should finish and then we can attack
Okay.
as much as we like.
Okay.
Because maybe in the next 3 slides we'll answer all our questions.
Okay, let's not the energy get drained now. We can come back with the questions at the end.
So
Why
you-
don't you?
I will shut up. Don't worry.
No, it's,
We'll come back. Manish, why don't you finish?
you want to say something?
In topological insulator, so bulk boundary correspondence doesn't mean that we are working with the same bulk and boundary at the same time. It just says that you have a infinite long system or you have that bulk property, and when you can't, then you get some non-trivial this stage modes or whatever, and that has some connection to the bulk you already kind of discussed.
So to understand, when I cut open the system in both x and y direction, and it's a finite system where I have a boundary here, and if I carefully look at the boundary, it is an effective SSH chain with a couple of defects. Simply the defect is like there is a defect we can see here, and there is a defect here and here. Here instead of a regular SSH chain with V and W as a hopping, our chains have this chain has a hopping V and T. So what we can do is we can write the Hamiltonian for this edge as a Hamiltonian of the SSH, Hamiltonian of the dimer, which is this one, and the connection between the SSH and the dimer, which is this one. So, and when I try to represent it in the matrix, and if I try to diagonalize the matrix, I'll have the energy spectrum like this. So interestingly, I can see there are 4 zero energy modes when the system is in V less than W, T less than V plus W by 2. When the system is in its trivial phase, there is no zero energy modes. And where are these zero energy modes come from? So I will look at the wave functions of the zero energy modes, where I can see these zero energy modes are coming from this isolated atom corner here, especially this isolated atom and this isolated atom. This will be where when V is equal to 0, extreme case. And a trimer is there in the system, 2 trimers, a couple of trimers are there in the system, where equally this one of the zero energy modes is localized here and here equally, and this one at here and here. So that is what this particular this thing says. So now I can establish a bulk boundary correspondence with a bulk winding number 2. I have 4 zero energy states. A bulk winding number 1, I have 2 zero energy states respectively. A bulk winding number 0, I have 0 energy states. So last week there is a Chinese group which do a similar kind of experiment for such kind of rectangular lattice systems with defects in their edges, proved our result to be like supporting our results experimentally by saying that localization can happen, and it is strongly localized at the corner states, which is in our case. So
What is the experiment?
sir, they used optics experiment. They used optics.
Some idea.
Sir, I didn't.
That was one of the questions.
Sir, this is the paper. I didn't give a reading at this paper yet. Not yet, sir. I will go. Last week it's happened.
No, it's good. They acknowledge it. Your paper is acknowledged.
Yes, experimentally they support our prediction. So, and I would like to acknowledge Rakesh Tibriwala sir, A.P. Balachandran sir, T.R. Govindarajan sir, Swavrao Basu, Arjit sir and Saptarushi from IOP, and Pankaj Balla and Sujit Sarkar for their valuable discussions throughout the journey. Oof. And these are our references. And thank you. Yeah. I thank my advisor for his patience towards me. So I will report in 1 week, within 1 week. It's on the archive. It's available in the archive.
Okay. Students' questions. 2 students. Now there should be some questions. Yes.
Only student class.
Yes.
Sir, it is realized in the experiments. Optics experiment, they confirm the localization and numerically said the corner modes in the experiments. Sir, some optics experiment with the T graphene lattice structure.
Ganesh can help you in understanding. Yes, students, any
faculty.
Others. While you want to questions.
I don't clear.
Now he will say,
No,
go read the paper.
It looks like they can
Paper
open
is,
up.
I don't know the relevance. So you say you cut the edges. So the real system is a cylinder,
Yes, sir.
not a torus, a cylinder. Because there is a two edges there. No, cylinder is a two-dimensional surface. So it's a two-dimensional surface. But certainly I can write the volume form. Volume form, if you integrate it, it is not zero, but it is closed. So I can write it d of something. Because with d of something, it will give two line integrals at the boundaries.
Hmm.
So that will be the value of the volume form as given by a line integral on the two boundaries with the negative sign. So the volume form integrated, it will be a topological invariance because the volume form, nothing will change. And the value of the integral on each of them, I don't know whether they are stable, but they will cancel. They will conspire to give what is in the bulk. You can call this volume form as an invariant, but I don't know how it is zero point.
Sir, but in this volume, when the cylindrical representation is happening, we are not completely exploring the bulk, right? We are specifically restricted for one particular direction to be open and one particular direction to be closed. So if I take kx to be,
So there is another thing. You can wind around the cylinder, you can go around. So pi one, there is first orbital group is not trivial. So you can always write a quantum state which changes by an arbitrary phase as you go around it. That phase there is called it can be integer, but it can be any angle. That will change the spectrum of the Hamiltonian. Only
don't think
for a
he has
particle on a
anything
circle,
like that.
it changes the spectrum.
He doesn't have anything like that.
Huh?
No,
He doesn't have anything like that.
what you have is a rectangle or square
yes, sir.
with periodic boundary conditions.
Yes, sir.
And when you try to apply the periodic boundary conditions, you will get the torus.
Hmm.
But now you have opened up the torus. But essentially, what is going to happen in the four corners
Yes.
of that is going to play a crucial role in deciding what are your topological features.
Yes.
That looks like that.
Yes, sir.
Coordinates.
Yeah.
Can I ask
Externally,
something? What are the tunable? Are the VW? Are those things tunable?
Sir, it can be tuned by doping the conductive polymers. GD can,
But is that what you have in mind? That when
sir, conductive polymers, 2000 Nobel Prize in chemistry. So,
Okay, don't bother yourself. Look at me and everything else.
sir,
Is that what
they
you
are
have in
tunable
mind?
by doping.
When you say that when V is less than this value,
Yes,
then you are in that
it can be done by doping.
When it is greater than this value, you are in southern. So that's what you have in mind, that you have different possible ways
Yeah,
of
the way we
different
dope the
values
system.
of-
Yes, sir, the way we dope.
You can just show me that table, no? This is good enough.
This
So-
is the torus 2D system.
This is good enough. So you can arrange for things so that V is less than W or V is
Yeah,
greater than W.
we can do it.
And when V is less than W, you have the first row. When
Yes,
V
sir.
is greater than W, you have the third row, etc. Is that right?
Yes.
So you are imagining that you are in a situation where V, W, and T can be tuned
Yes.
in some sense.
Yes.
And when you tune them, you are in one of the four situations. As you tune them, you
Yes.
go from
Yes,
first
yes.
situation to second situation.
Yes,
etc.
yes,
That's
yes.
what you are- that's
Yes,
what you're saying.
yes, yes, yes.
It's a way in which temperature or something can change the value of
Sir, we didn't look in the direction of
So that
temperature
could
yet.
be a phase transition.
There may be a phase transition. Okay.
That is the kind
So
of.
we will-
Doping is not the only thing. You can actually apply facial also.
Yeah, stress and strain on the system can also do.
But for SSH model, the experimental realization doesn't need this polymer stuff. Right now, there are
So since we are theoretical, we didn't look in that direction. But I just went to this conducting polymer paper where we see because of the doping we can have the conduct where this.
applying the pressure also you can change the.
Yes, sir, we can change it. But the first thing in my mind is the doping thing I got. Yes, sir. SSH is the polyacetylene chain. Sir.
So what is the exact statement that some of these operations
Sir, so these operations will give a restriction on the phase evolution of the system.
So what I'm sorry, the time reversal and
Chiral symmetry and parity symmetry.
so what's the statement? If I'm on a torus, I open a torus, then
Sir, I will use these expressions, these expressions. Okay, and I'll try to what I can do is if I can see how these expressions will change. Okay, I'll see the vector of this sigma hx, sigma x, hy, sigma y, the vector what I have. Then what will I do is I'll try to change v, w, and I'll keep them as constant. Now because of this certain symmetries in the system, we can see this for a positive, for kx and ky equal to minus kx and ky, we have the same vector. So such kind of cancellations or such kind of things comes when there are certain symmetries in the system. So because of that, we try to derive a topological invariant. Like this is how they classified, the community classified, and we follow the structure.
just if you're on a torus,
Yes, sir.
but your Hamiltonian required to have this symmetry, then you are saying that some invariants are ruled out. or
Yes.
That's the statement.
Any other questions,
Basically, I
comments?
think the properties of the two V and T, they become or remain unchanged.
Yes, sir. There will be a minus or plus sign where because of v, t, and w play.
S, C, and
T.
T.
Yeah.
Yeah, I was just looking at like
Sir, but v minus double.
But they have certain properties.
Sir,
They
even
have certain properties under those three symmetry transformations.
sir, I can tell here under certain symmetries these things will be there, and depend on the condition of v less than w, t less than w, there might be a minus or there might be a plus. I did this for SSH model where I have the idea of how this minus and plus and this symmetries will play the role. So in one of the path, this one at this point hy is completely zero. So at this direction we are unable to find a topological, like unable to find a path because it won't bind anything. It's only hx. So there is this thing.
No, I was looking at notes of Sodom Storm.
Yeah.
He said +1 means it is symmetric under the transformation, -1 is anti-symmetric, and 0 means no symmetry. Not that they haven't found any symmetry, there is none.
No.
No, I'm very sure.
No. I will tell. So this is what SAR says: +1, -1, 0 in here, in this one. Not the 0 is from the dimension 2. We don't have a topological invariant. It's a trivial this thing. What Saurasar's statement is.
It's not that it's not been found. You said like 0 is not yet found.
I'll say it's
Then
rephrased it like it's.
Sorry. I missed that.
Okay.
And thanks a lot to Rakesh sir for giving the opportunity to present our work, and my guide for the patience.